All right, I'm going to, oops, hold on. This is all kinds of stuff that you don't care about. Here we go. I'm going to call this part 2. I think I'm not a real expert on recording videos on my laptop screen yet. And so I'm assuming that this will actually start a whole new video. So I'm going to call this one part 2. And it's actually, Anthony, if you're watching this, you're the one that just interrupted me. All right. So quite all right. So I'm basically continuing where that first one that we started building this falling sphere model left off. And I think I left off with saying that we have, let me see, we have our parameters defined we're using. We've got the arrays that we're going to use allocated, and we've got some initial conditions specified. Now we're going to start the iterative process, and the way you do that in a programming language is through a loop. Here is the Matlab format for the loop. We need a dummy index called a for loop, right? We need a dummy index. I'll use I. It literally is a dummy index. It's just a way to index values within the loop, all right? And we're going to do this, and I'll show you why in a moment, why we're going to start with 2 to n. Now remember we specified n up here. Let me scroll up and show you n here. Yeah, right here we specified the number of iterations. But I'm only going to start from 2. That'll be obvious in a moment. And then I'm going to put my n. So everything in between 4 and n, that's part of the loop. And it will be done as many times as I tell it to. So it'll start with index 2 and it'll do it until it gets to 1,000. If I don't have any other numbers here, if I just have 2:n, it will increment by default one value. So the first time I will be 2, it'll do stuff inside the 4 and end. Then it'll come back up, I will be 3, it'll do some stuff, I will be 4, and so on until it gets to 1,000, because that's what we specified n as. Alright, so the first thing we're going to do, right, what we got to do in the loop, this is where we actually calculate for each successive time step. We calculate all the values that we want to have calculated. Some of the values are going to be exact values. Some of them are going to be updated according to our approximation. Right? Let's start with time. All right. I'm just going to do this. Time, and look what I'm doing. All right. I'm going to use that index, and I'm going to assign time of I minus 1 plus dt. All right, now let's think about what this is going to do. All right, type that in and take a look. All right, the first time I jump into the loop, I will be 2. That's the first value of 2. So look what this is telling it to do. Time of I is 2. Time of 2 equals 2 minus 1 is 1. So time of 2 equals time of 1. Now look, we already have time of 1 defined before we jumped into the loop. That was the initial condition up here. So this says time of 2 equals time of 1 plus dt. So basically this increments time by 1 time step, dt. See how that works? Okay. Now you can imagine jumping out and going back up. Now I will be 3 the next time through, and then it says time of 3 equals time of 2 plus the increment, right? So this, I believe, successfully does what we want it to do. This assigns each successive memory location that's associated with the array time. It assigns it the next time step. So I think you're getting a feel for how this works now. Right now what we're going to do is use that simple Euler method to update the position and update the velocity. All right, so the first one is going to be position. Position of I. Now I think it's obvious why I started with 2. See that? Position equals position of I minus 1. All right. I started with 2 because that's the next time step that I got to define. We already have time, position, velocity, acceleration of 1 defined. All right. That's why I started the index I at 2 here. So I could use this I and then I minus 1 on the right hand side. Well, the Euler method gives us the way to update position. The Euler method says position at the later time equals position at the earlier time, and if you need to, go look at the equation. Let's go down one slide. Here's our Euler method, remember, down here. Both of these equations here. Position at the later time is approximately equal to position at the earlier time, and just do what it says to do, plus velocity at the earlier time, that's the previous velocity times delta t. So we go back to our script here, plus velocity of I minus 1 star dt. Don't forget the semicolon. So that's the Euler method applied to position. Now this is an approximation, remember. So you can think of this as updating or accumulating position based on that simple Euler approximation. So everything on the right-hand side is at the earlier time step, and everything on the left-hand side is the current time step within the loop. So in other words, position of 2 will equal position of 1 plus velocity of 1 star dt, and we have velocity 1 defined already as the initial velocity. See how that works? Let's do velocity. It will look almost identical to what we just wrote for position. The velocity at the next time step, which is the current value I, or 2, the first time through the loop would be 2, equals velocity at the previous time step, so I use the indexing scheme, I minus 1, plus acceleration of I minus 1, star dt. See that? Again, I'm using this equation as a basic Euler method. The velocity gets updated in a similar way. Velocity at the later time is approximately equal to the velocity at the earlier time plus acceleration at the earlier time times dt. All right, and that's how it looks. Finally, before we jump out of the loop, acceleration at the current, so we want the current acceleration. All right, but keep in mind, this is not an approximation now. Go back to our model and go up one. Remember, this is the acceleration. This is the exact expression for the acceleration. And A of t is evaluated using v at the very same time step. See that? All right, so in our loop, here's what we got to do. We've got to write it like this. Matter of fact, the easiest way to do it would just be to copy this equation that we used for the initial acceleration, and instead of 1, this would be velocity of I, because we're inside the loop. Let's do that. So I highlight this. I'm just going to do a copy and paste here, and instead of 1, I do an I. See that? Remember, we're not approximating acceleration here. That's why I'm using I. I'm not using I minus 1 on the right-hand side. This is subtle, but make sure you understand why. Okay, acceleration is exact. The expressions for position and velocity in the loop are approximations, right? That's why delta t has to be small, but the acceleration is exact. Time is also exact, by the way. We're not approximating time. We are approximating position and velocity, however. All right? Okay, now, that's that. Now, we could let this run, and it'll do all of this stuff, and it'll store all these values in the array. So if I run it, let me just go ahead and run the thing. Now nothing interesting will happen because we're not outputting. I've used semicolons to terminate all the output. Okay? And so nothing really interesting will happen, although a little bit interesting will happen. I'll show you what's interesting. I click the little green button at the top, run. All right? Now again, nothing magical happened, but if I go to that command window, back over here to the command window. All right, now I didn't output anything, so it looks like it's still at the starting point, but look what happened over here. Do you remember over here on the right, this is this workspace. It's called workspace. This is where the values of all of the parameters we used show up. All right, now let me point out a few things here. And this is going to be useful to point out a couple things. All right, let me move this over so we can see all this. There we go. All right. So look, first of all, you'll see some of these actually under value column. So there's a name column. Variables show up as we define them. And then there's values associated. So for instance, dt. Remember we put 0.1 for dt. There it is. G is our friend, 9.8. It shows the last value of I because it ran through that loop. It went from 2 to 1,000. It's actually showing the last value that I had the last time through the loop. There's m. Okay, so all of these things. Now look at acceleration, position, time, and velocity. They all don't have values, but you notice it says 1 by 1,000 double. That's because acceleration, position, time, and velocity are all arrays. They all have 1 row by 1,000 columns of information or values. Now it doesn't display the values. If you wanted to see them, you can actually take a look. If you highlight this in that window, and I think if you double click, I believe it opens it up here in the command window, right? And so, of course, there's 1,000 values. Of course, it only displays so many at a time, but you can see what the different values are if you just scroll along. Okay, you can see what they are all the way out, and they're all numbered. See that? And you can see it stops at 1,000. Okay, if we did the time, let's have a look at the time array. Time, of course, starts at 0. That's the initial time, and we're incrementing by 0.1 every time. So time's easy to see that it's correct. See that? And since we've done 1,000 arrays, and we've gone, or sorry, 1,000 values in the array, and time is incremented by 0.1, that means we should end up with about almost 100 seconds altogether. We get 99.9 because remember the first one was 0. And so the 100th, or the 1,000th time step is actually 1 delta t less than exactly 100 seconds. Anyway, that's the information you have in this workspace. So without outputting anything, the workspace just tells you what the values stored are. You can take some time to read about this if you want. The size just tells you a scalar number is a 1 by 1 is the same as a 1 by 1 array. You know, Matlab was created to deal with arrays. Matrix Lab Laboratory. Matrix Laboratory is what Matlab means, right? So Matlab thinks everything's a matrix. A scalar number is a 1 by 1 matrix, believe it or not. An array, a vector, is 1 by 1,000. That's a 1 by 1,000 array. Bytes is the total number of memory associated with all the values here, whether it's a scalar number or 1,000 of these values. And class is the type of number. We'll talk more about this. Don't worry too much about this. Double means double precision. It's the type of value that is represented by default for Matlab values. We'll go over that later. All right, so let's close that. Now, if we go back to the script, let's say we want to actually plot this. All right, that we have used arrays makes plotting really easy. Okay, so if I do this, plot, literally the command plot, and if I do the following, time, and let's plot velocity first. If you haven't yet, take some time with some MATLAB tutorials on plotting. It's very easy to get down. If I put arrays inside here, then it will use every successive memory location in each array and plot velocity versus time. Listing time first, all those values will be the x components, or the coordinates, and the velocities will be the y components, or the y direction. So this will plot every value in the velocity array as a function of every value in the time. So this will should produce a plot of velocity versus time. And look what can happen here when I hit, if I don't terminate it, actually if I do terminate it, I think it'll still plot because I'm commanding it to plot. So if you hit run, look what happens. And for some reason we're slow, but the figure should pop up, and look what we've got. Right? You can see this is the velocities of function time. Now, we haven't investigated whether this is accurate or not yet. All right? And that's going to take some doing, but right now, this should, we can at least see if this makes qualitative sense. By qualitative sense, I mean, does this behave like you would expect the velocity of a falling sphere dropped from a high distance to behave? First of all, you can see from 0, all right, let's zoom out a little bit. Okay, so from 0, starts at 0, 0, and the curve increases rather rapidly. See that? As time goes on, even up to about 5 seconds. You see the time scale here? Now there's a couple ways we could zoom in here. You could change the scale. You can do that directly on here, or you can use this little magnifying glass thing to zoom in. Let's do that. If you make a little box, it'll zoom in on the plot. So that's a little easier. So instead of plotting out to 100 seconds, I'm plotting out to, I don't know, 16 or 17 seconds now. I'm going to leave it to you to figure out the easiest way to zoom in and out of these graphs. All right. So remember, this is velocity in meters per second versus time. So you can see the initial rapid increase, and then it levels off, starting around, I don't know, 3-4 seconds. It levels off rather rapidly and then becomes almost constant. Right, now, is that what we expect? Right? So if you, let's not take time to do it, but if you go back and you think in terms of your physics mechanics course, all right, or who knows, I don't know, maybe you saw this in an engineering class somewhere. The whole idea of a drag force is that it will actually grow as something speeds up. So if you look back at the resistive force we're using here, there's two terms in the acceleration. There's the gravitational term, which is constant, but this term, the drag term, depends on velocity. So if you drop a ball, of course, the drag term starts out small because it's not moving, but as it speeds up, the velocity increases, so this whole term will start to grow, and eventually, if it's allowed to fall far enough, this term will grow to match the constant term, and eventually the acceleration goes to 0. So what we're looking at here makes perfect sense for a ball falling in a fluid or experiencing a drag force. The fancy name for this leveling off is called a terminal velocity. In other words, it simply stops accelerating at some point because of the drag force. Right? And you can see the approach to the terminal velocity. It bends over. So this is acting qualitatively perfect. This is exactly what we would expect for a falling sphere. Right? If we wanted to go back to our program here, now we can play with anything. We could plot, instead of velocity, let's plot position. All right? And also, now there's ways to limit what we plot here. Remember when I zoomed in on that last one, it looked like the interesting behavior was done by maybe 15 seconds or so. So there's an axis command. Let's just do this, and I think x-axis command. I think this will work. If not, we'll find out soon enough. And all I'm doing is telling it to, plot, hold on. 0, let's see if this works. I'm trying to tell it to plot a specific, that might not, you know what, that might not be right. Let's look this up real quick. Let me just demonstrate for you how to look things up real quick. Axis command, Matlab. See, I don't remember these things. I program in a lot of different languages, and I really just don't remember my my syntax here. Limit, I think. Xlim is what we're after. I think that's what we want. Let's try that. XLIM. You can see how easy it is to get to this stuff. Yep, XLIM. That means X limit. And so let's look at an example to make sure we get the syntax right. Excellent. So the round. So here we go. I'm just going to copy this. Copy and paste. Aren't computers great? All right. So you don't have to memorize this syntax. You just look it up and you got it, right? So what I'm doing is limiting the x-axis, the time axis, right, to 0 to 15 seconds. So now I'm plotting position versus time, but we're only going to go out to 15 seconds because that looked like the interesting region anyway. Now this is position in meters, time in seconds, and look how it's behaving. Now look, it almost looks parabolic in here, right? It shouldn't it? Because for at least really, really small times, the drag term has not increased very much, and so it looks more or less like a free fall for the first, I don't know, half second or so. So this is rather parabolic, but you can see very quickly, 3-4 seconds, that's starting to straighten out, and it's almost linear now, which a linear position versus time, you may remember, is consistent with a constant speed or a constant velocity graph. Right? So at least with this value of 0.1, this looks at least qualitatively correct. Let's do one more little thing here. Let's look at acceleration. So I just change from plotting position or velocity, let's plot acceleration versus time. And let's have a look, and there's the acceleration versus time. Now it's interesting, you might not predict that there would be this inflection here, but you can see as time goes on in the neighborhood of 5-6 seconds, that acceleration is pretty much gone to 0. Right? Which means the drag term is caught up and is matching the gravitational pull downward, and so we're no longer accelerating. Constant velocity, linear, position versus time. Right? So everything's consistent, looks pretty good. Now, is this an accurate solution though? That's what we really have to grapple with. All right, and so let's do the following. Let's add the exact solution. Remember, I said that we have the luxury of having a calculus-based exact solution we can compare this to. Now remember, we only have an exact solution because we're pretending d is constant. All right, and as you're going to discover in your first project that we really can't let d be constant. All right, but we'll pretend it is. Let's actually program this thing into our script here. All right. Okay. Now I think actually I'm going to take a little break, so this will be done in video part number 3. All right. Stay tuned, or we'll close this one out and then launch video 3 to see our comparison with the exact value.